All right, let's take some time to work together some practice problems related to sets of real numbers and classifying real numbers, and then the concept of intersect union and counterexamples, potential counterexamples for statements about closure. All right, so let's start at the beginning. For each number in A, B, and C, we need to identify the subsets of real numbers to which it belongs. So it's not just going to be a single set or subset. We have to identify all subsets. What about negative 73? What kind of number is negative 73? Well, I know negative 73 is an integer. Because it's an integer, I know it's not a counting number or a whole number. Okay, because counting numbers and whole numbers don't include the negative numbers. So I have to start at integer. But if it's an integer, it is also rational. And if it's rational, it's also real. However, because in the instructions it says the subsets of real numbers, I don't have to list real as one because I'm already identifying that it's real because it's a subset of the real numbers. So this is an integer and a rational number. What about the next one? 5/9. Well, looking at 5/9, I know it's not an integer because integers are whole numbers and then the opposites of the natural numbers, but nothing about fractions in there. So this one's just going to be a rational number. And then what about 18 pi? Well, pi is one of those values that's not rational. We say that that's irrational. So we would say that 18 pi is an irrational number. And you'll know irrational numbers because they'll either have pi in them. They could have another constant, but I don't think Saxon's going to include any of the other constants other than pi. That would be irrational. But the other thing that they will include sometimes are square root symbols on numbers that can't evaluate to just a single square root, like the square root of 2, or a cube root symbol or something like that. So this is an irrational number. And again, it's a real number, but these are all subsets of real numbers, so I don't have to list reals. If you wanted to list reals, you could, but you don't have to. All right, next, identify the set of numbers that best describes each situation. Explain your choice. The number of people on a bus. Let's see. Well, can we have 0 people on a bus? Yes, if the bus is sitting in a parking lot without the driver even on it yet. Can we have 1, 2, 3, 4? Yep, we can have counting numbers of people on a bus as well as 0. And then can we have fractions of people on a bus? Not really. There's no realistic way to do that. So the set of numbers that best describes a situation, the most specific set of numbers would be the whole numbers because I can include 0 and the counting numbers. All right, what about the area of a circular platform? Well, anything that involves area, let's see, when I have the area of something, area is calculated of a circle, pi r squared. And anytime I involve pi, I have an irrational number. So I can't represent the area of a circular platform with a fraction because it has pi in it. Pi r squared, that's the formula. Remember that, by the way, the formula for area is pi r squared. The formula for circumference is pi times diameter. Anytime you see circular, that should throw up red flags that you're probably dealing with something irrational. The value of coins in a purse. Okay, can the value of coins in a purse add up to 0? Yes. Can the value of coins in a purse add up to a whole number? Like if I have 4 quarters? Yes. Can it add up to fractional numbers? Yes. What if I have just 1 quarter? $0.25. Hey, can it add up to an irrational number, like a number that's a square root or multiplied by pi? No, that doesn't make sense. It's always going to be some fraction of 100, right? Some fraction of, because 100 cents is a whole dollar. So the value of coins in a purse is going to be rational. Now you could make an argument that in cents, if you're adding up just cents and not the value of dollars, cents, it would be whole numbers because you could have 0 coins in a purse. And you could have a positive number of cents, but you're not going to go you don't have negative coins or anything like that. All right, whole, irrational, rational. I prefer rational as an answer for this one, by the way. That would be entirely based on your explanation because it says explain your choice. So you could explain that it could be a whole number, but you'd have to explain it. All right, so for letters G and H, I'm asked to find C intersect D and C union D for each of these. I brought in my intersect and union characters that I'm going to use to answer these questions. So the first thing I'm going to do is I'm going to create a text box, and I'm going to say we're going to do, first of all, C, and we'll choose to do intersect first. I'm going to copy this. I'm going to paste it in here. C intersect D equals. Now, I need to look at the elements that are in both C and D. And what do I have here? 4 is not in both. 8 is not in both. 12, 16, and 20. It looks like the only number that's in both 4, 8, 12, 16, 20 is the number 20. So C intersect D would simply be the number 20. And then I'm going to grab my union symbol here, and we'll go ahead and do C union D right away. So I'm going to do some spaces, C union D. The set C union D is, in set notation, I need my squiggly brace, is going to include all of them. 4, 5, 8, 10, 12, 15, 16, and then notice 20 is in both sets. I actually only have to list it one time. So it's going to be 16 and then 20 and squiggly brace. Let me just make sure it all fits on one line there. And there we go. So that is C union D and C intersect D. Let's go ahead and do the same thing for the sets down below. I'm just going to copy and paste this and we'll adjust it. So C intersect D. Let's get rid of this 20 and let's get rid of this whole line of elements there. And let's see which of these elements are the same in both sets and different. So as I look for what's the same, 6, 7, 12, 14, 18, 24. There are no elements in common. That means that C intersect D is the empty set. I have to write it out just like it is. C intersect D, and then my squiggly braces, but with nothing inside. That's the correct way to write that. I could also write a circle with a line through it. I don't have that character pulled up. Here, let me see if I could find it. Empty set. And the symbol for the empty set is the Greek letter phi. So I could also say that instead. So it'd be C intersect D equals that. Okay, those are the two ways of writing that it's the empty set. Now, what about union D? Well, that's going to be all of them. So 6, 7, 12, 14, 18, 21, 24, and 28. Okay, and again, let me just make this long enough to fit all of them on one line. And that's the answer for H. Empty set for C intersect D, and then all of the values in both sets for C union D. Now, let's take a look at the last part. The set of whole numbers is closed under multiplication. Is that true? So let's think about that for a second. I'm just going to write true for now, just in case, and I'm going to drag that down. Is that correct that this is true? Well, if I take two whole numbers, 0 times 5, do I get a whole number? The answer, yes, because 0 times 5 is 0, that's a whole number. 0 times 20, yes. 20 times 20, 20 times 5, 20 times 8. Let's try really big numbers. 1,000 times 20,000. It's always going to be a whole number. So whole numbers, the set of whole numbers is closed under multiplication. That's true. What about under division? Well, let's think about this one. I'm going to say this is false right away because it's really easy to come up with a counterexample. For example, what about 5 divided by 6? 5, 6 is not a natural number. This is natural numbers, okay? So I have to use the counting numbers. 5 divided by 6 is not a natural number. It's not even an integer. It's a rational number. It wouldn't be considered an integer or a whole number. So it's easy to prove that the set of natural numbers is not closed under division. Division tends to break the rules for closed sets. It's sort of subtraction a lot of times. So watch out for subtraction and division in these situations. Subtraction, by the way, won't break the integers, but division will. Division changes things from integers or whole numbers into rational numbers.